Good morning. Let's continue from where we left off last time. So we were looking at fin, and we looked at certain parameters that could be used to quantify fin performance. So we looked at fin effectiveness and fin efficiency. But now I want to bring your attention to a more relevant situation where you need to understand that we looked at a single fin, and we don't look at, I mean, in a heat transfer problem, it's not just a single fin that transfers energy. It is also energy is also transferred from the base on which the fin is attached, and you never see a single fin in practice. You will see, many hundreds of fins put together. So you want to use that idea to define something called as an overall surface efficiency. And to describe what this efficiency is, so if you look at this array of fins, okay, so let's say you have lots of fins put together on a surface, and we have some geometric features associated with these fins. For instance, their thickness is, I said, is t, and let's say that the pitch or the distance, the periodicity of these fins is, let's say, s. Okay, as usual, they are surrounded by a fluid which is convecting heat away from this surface, and I'm going to assume that the temperature and the heat transfer coefficient is the same everywhere. We had other geometric features. For instance, we had said L is the length, W is the width, okay. Now, for this kind of arrangement, there are two surfaces from which heat transfer will actually take place. One surface is of course the surface of the fin, so which I can maybe describe, by this area. If you see, right, it is this area and this area, and of course maybe this area and the bottom area, and so on and so forth. So all these areas are contributing to heat exchange with the surrounding fluid. But in addition to this area, there's another area which is also contributing to this heat exchange, which is this area of which I'm going to call as the base, or the actual surface on which these fins are mounted. Okay, so these are also contributing to heat transfer. So to quantify the total heat transfer from a fin, we define this number that I'm saying now is overall surface efficiency, which I'm going to denote by eta naught. Okay, and the way we are going to define it is, we're going to say that it is going to be, we need to look at what could be the maximum possible what is the actual heat transfer versus what is the maximum heat transfer that can take place ideally. So eta naught is the actual total heat transfer from the entire fin array versus the maximum heat transfer that can be taken out. Okay, and to calculate the maximum heat transfer, we need to realize that the temperature, we specified a few things when we were doing this analysis. We specified that the temperature at the base of the fin, we said, was TB, but that is also the temperature of this surface, which I'm going to call as a prime surface, okay, or the the base surface. So both surfaces are actually going to be at the same temperature, except in the case of fin, TB is the base temperature, and because of conduction, the temperature decreases along the length of the fin, but the base is still at the same temperature. So I can define this number eta naught to be Qt by H, as I'm assuming H is always the same, total area, which is the total area which is of the base and the fin combined, times the potential or the temperature difference, which is theta b. So keep in mind, AT is the total exposed area, and now we're not dealing with just one fin. So how do we write this total exposed area? That we can write in terms of the fin area, as I've shown in the base area. So I can write that AT should be the area of the base plus, let's say, area of the fin, and assuming each, let's say there are n fins in the geometry of the same type, then we have n times AF. So that would be the total area that the surface shows up for heat transfer. Similar to the concept of area, we can also write heat transfer. Now remember that there are different modes of heat transfer from the base and the fin. From the fin we have heat transfer because of convection, or rather from the base we have heat transfer because of convection, but through the fin we have heat transfer because of conduction and convection. So there are two paths for heat transfer. So QT, which is the total heat transfer, will actually be Q from the base, and the base is not just one base. I mean, I should not say that. Don't assume that QB is just one area. It takes into account all these areas. 1, 2, 3, and whatever areas are there in the problem. So QB plus the n times heat transfer taking place from each fin. So that would be the total amount of heat transfer that we should expect. Now here I can invoke the definition of the fin efficiency. So we can write this as, and also the definition of QB. So remember, QB would be just H, because I said it's only heat transfer because of convection. So that should be HAB into theta B, because that is area times the temperature difference, plus n times, what was QF? QF could be written in terms of efficiency eta F times H, area of the fin, times theta B, where eta F now combines, what is it looks at the relative, it looks basically quantifies the conduction resistance offered by the fin. So what I'll do is I will combine now these two equations. I will combine this equation with this equation and write a new equation to somehow, get out or get eta naught, the surface efficiency. So what we can do is, or what is typically done is that we can write AB in terms of AT and AF. So I write this as H theta B, AB becomes AT minus NAF, and this is anyway N eta F HAF theta B. And then by just doing a very basic jugglery, so I can pull out some terms, and just by taking some fractions, I can write that this QT will be H theta B AT. Remember, there's H here, theta B on both sides, so that is common. I'm going to pull out an AT, so we'll have a fraction of AF by AT. So this becomes 1 minus NAF by AT times 1 minus eta F. So QT could be written in terms of the individual fin efficiency and the fin area and the total area. And so the surface efficiency, which is QT by HAB theta B, is just 1 minus NAF by AT 1 minus eta F. So knowing a single fin efficiency and the geometry of the problem, okay, we can actually determine the overall surface efficiency, or vice versa. If we know the overall surface efficiency, we can even look at what would be the efficiency of a single fin. The predominant use of this expression is in that if you know eta naught somehow, if you have somehow figured it out, then it's easy to calculate the overall heat or the total heat transfer, because QT then becomes just eta naught times HAB theta B, HAT into theta B from this equation. So once you have eta naught, you can straight away calculate what would be the total heat transfer taking place from this fin and this from this equation. That is one of the main reasons for using this. Okay. Now, similar to what we've been doing for resistances, we've been trying to represent all heat transfer processes where there is no heat generation. We've been trying to show that in terms of thermal resistances. The same can be done here. I can define an overall thermal resistance, let's say RTO. So this is the effective resistance that would include both pathways which are convection from the base surface, and uh, conduction and convection on in the fin. So this we can write as theta b by the rate of heat transfer, which is qt. And so this becomes 1 by eta naught hat. That is just from the definition of the overall surface efficiency. So what it means is, remember, theta b is the potential difference, q is the current. So in terms of circuits, we are saying that the heat transfer takes place between Tb and T infinity. Qt flows through this segment, and the resistance is 1 by h eta naught hat. Equivalently, this is something that I would request you to, I request you to go and check and prove this to yourself. It does hardly takes like a minute to do this. I'm deliberately skipping it from this lecture. So equivalently, you can also prove that this circuit is the same as as heat flow between, or total heat getting split into two parallel resistors. So equivalently, this would be the same as heat flow from Tb to T infinity, except one side the current I can write is QB, and the other side I can write the current is NQF, which is actually, if you uh, want to know why I have drawn it this way, you can see this equation, this one. So it's saying that the total current is a sum of the base current plus the fin current. So it cannot be through the same, if the current is adding, that means you must have two parallel, resistors. So you have two parallel resistors. On one of the resistors QB goes, the other resistor NQF goes, and then it's just something for you to derive that the resistance is associated with each of these heat currents would be that for the fin, it would just be 1 by eta f h af, or times n. I should not forget n, because there are n of these, n times n. And for the base, it would be 1 by h a b, which we can also write as 1 by h times at minus naf. So the second one is resistance, what I'm calling from the prime surface, okay, or heat flow through the prime surface. This is heat flow from the prime surface, which is also the base. And the first one is essentially combining resistance from both conduction and convection into one quantity. So this sort of concludes our discussion on extended surfaces. There are many more issues to be tackled in this. There are some nice examples given in the book. I would request you to look at them. Anyway, we'll do some problems in the tutorial, which will also give you a flavor of how these kinds of calculations are done and how these fins are designed. But I strongly request you to look at the book. And then there is one more issue. Even in fins, there is one additional aspect that we have looked at fins being part of the base, but sometimes fins are actually attached. So the fin could be of a different material as the base. And so when you put them together, you can actually have contact resistance, which I have ignored in all my analysis. So that can also be accounted. It is slightly more, there's one more additional equation that needs to be written. It's available in the book. I would request you to go and look at it. As a designer, I think you should know that this can also be tackled. For the purpose of this, first course in heat transfer, I will not be asking any questions related to fins mounted on a base surface. There are some other issues associated with it, and so I don't want to go very deep into it. For the purpose of this, at least for now, it's good if you know this much, that how a fin works, what are the different modes of heat transfer in a fin, and how can you do a very basic analysis or a very basic calculation to quantify whether a fin, is it effective or not, or whether it has a required efficiency or not. Okay, so let's move on. So here so this was actually the last, or not the last, I would say, but we'll take a break from one dimensional heat transfer at this point, and I'll discuss higher dimensional heat transfer. So I will look at one problem which pertains to two-dimensional steady-state heat transfer. And this course is primarily, it works on assumption of 1D analysis. But here, this is a place where I'm going to take a small break and just talk about steady, what happens in two dimensions and three dimensions, and how do we obtain solutions in those problems. So, and the reason for choosing this is because 1D analysis is simplistic. It makes many assumptions that may not be valid. And to show you why it is simplistic, let's take this case where we have, let's say, a plate, okay, which has some length and some width. So let's say the length is L, and let's say the width is W. This plate is actually, let's say, exposed to certain temperatures. So this surface is exposed to T1. This is exposed to some temperature, again T1. Similarly, this is exposed to T1, and the top surface is exposed to, let's say, T2, where T2 is not the same as T1. So T2 is not the same as T1. And say the question is that, what is the heat transfer rate through the top surface, because it's at a higher temperature. Let's say T2 is more than T1, or I should also define that. Let's say T2 is more than T1. So the question is, what is heat transfer rate through the top surface, and what is the temperature distribution in this system? Let's also take, for solving this problem, let's say Q dot is 0 and the conductivity is constant. And we are concerned with, or we are interested in the steady state temperature distribution. So I'm not concerned, what happens when the temperature on one surface is exposed, let's say increase, maybe, initially everything was in T1, then suddenly you made it T2, and so what would be the response? So I'm not very concerned with that right now. We are far, far away from, that initial transient period. Okay. So now there are some things that you may try and understand. Please observe this. See, if these two surfaces, these vertical surfaces, if they were insulated, I could have probably assumed that it's a one case of 1D heat transfer, and so I could have drawn that the heat, the heat flow lines would actually be completely vertical. So heat will only travel from top to down. Okay, but they are not insulated, so there can be heat transfer. The second thing I can maybe, as a beginner, I may assume is that let's not worry about what happens on the two surfaces. I just see a temperature difference, so I expect the heat flow to happen here, for the heat flow lines to be vertical. Okay, so something like this. Let me also draw while we are doing this. So let me say that as a beginner, I assume that heat maybe is flowing like this. Okay. Now the problem is that, as you can see, if heat is flowing in that direction from T2 to T1, there is also these neighboring surfaces where the temperature is lower. So quite, understandably, and I hope that you can also see this, it cannot be all vertical. You should be able to see something like this. You should be able to see some heat flowing maybe out, maybe something going straight. Okay, so that is something that we can expect, that we will have two-dimensional effects now. Heat will flow out of the three surfaces. How would it, which way it will go, more or less, that is something we want to quantify eventually. So these kinds of two-dimensional problems, they are not all problems have simple solutions or analytical solutions, but under some special cases, we can derive an analytical solution to these problems. And I can guarantee that you have done these problems in mathematics in the differential equation course on in the first year mathematics. I'm just going to show you how that what you did there is now applicable here. Okay, and that is some just I'll spend about 15-20 minutes to try and prove that what you did there is straight away useful in these kinds of problems. So before I work out the solution, let me start with some, setting up the problem in the right sense. Let's say we have the coordinate system defined. We define x here, y here with the origin at the corner. Okay, we know the dimensions of the problem. So we know L and W are the dimensions of this solid. So what is the governing equation that we need to solve? So we need to solve d by dx of k dt dx plus d by dy of k dt dy. Heat generation is 0, so that becomes 0, and it's steady state, so the right side is also 0. So that is the equation we want to solve. Now k being a constant, it actually can be pulled out from the differentials, and so what you get is d to t dx square plus d to t dy square to be 0, subject to the boundary conditions. We have t at, let's say, x0 for all y to be t1, t at, let's say, xl for all y is also t1. We have t for all x at y0 to be t1, and then finally t for all x at y equal to w to be t2. Now, what is typically done in these kinds of problems? And by the way, we are doing this because this is a simple geometry. It's a Cartesian geometry, so the edges are aligned, or we can at least, it doesn't need to be that it has to be. I mean, it's just a geometry which is rectilinear, so I can easily define my coordinate system and solve this in this manner. And the other special thing about this is that the boundary conditions are fairly simple. I have been given temperatures, and specifically in temperatures, I know that there are three surfaces which have the same temperature. So I'm going to exploit this aspect in trying to obtain a solution using the analytical way. So what I'm going to do is I'm going to define a new variable, which is theta, let's say. So theta is going to be a variable that I'm going to use, which would be defined as t minus t1 by t2 minus t1. So I'm going to define theta in this way, because I know that by doing this, and as you can see, there is no heat generation. So the maximum temperature can be T2, minimum will be T1 in this problem. So by doing this, I can ensure that theta is a variable which is always between 0 and 1 for all x and y in this, for all coordinates in this domain. So it becomes a value for all x comma y. So it becomes a value which is bounded within this range. And by doing this, I don't incur any change in my governing equation, because you can see that T2 minus T1 is a constant. So clearly, the governing equation would now be just d2 theta dx square plus d2 theta dy square is 0. And more importantly, the reason I did that was because if I look at the boundary conditions now, I have actually three boundary conditions which will now become homogeneous. So we will have theta at 0 comma y to be 0, theta at L comma y to be 0, theta at x comma 0 to be 0, and finally theta at x comma w is 1. So I've homogenized three boundary conditions. So we have these homogeneous boundary conditions and a homogeneous differential equation, and there is only one non-homogeneous term, which is the theta x comma w is 1. So now this becomes easy to solve using the method of separation of variables. So we'll employ the method of separation of variables to determine the solution to this problem. And the method of separation of variables is quite easy to understand, but the basic sense is I assume whatever variable I'm trying to work out, and let's say it's a function of x comma y in this case, I assume that that function can be split up into that many number of functions in those space variables, and those functions are only dependent on one space variable. So for instance, I can write here theta of x comma y is a function of x and a function of y. So capital X, which is a function of x, capital Y, which is a function of y. Whether this is really true or not, we will see. Upfront, we cannot say anything, but we are assuming this. So let me say this. This is another assumption that I'm making. Whether it works or not, it depends on a host of conditions, and we'll see why when it works and when it doesn't work. Of course, in this case, it works. That's the reason I'm doing it. So anyway, so if I assume this and put this thing into this equation, I can then derive the modified governing equation. So I will have, remember, d2 theta dx square would now just have x d2x dx square, and d2 theta dy square will have just d2y dy square. So we'll have y times d2x, let's say dx square, plus x times d2y dy square to be 0. And I can then rearrange and write this as 1 by x d2x dx square to be equal to, let's say, minus 1 by y d2y dy square. Now I come to the reason why we did this whole exercise. I can see that this equation, or this left hand side of this equality, is only a function of x, small x I should say, and this right hand side is only a function of y. So clearly the only way these two will be equal to each other is if they are equal to a constant. So these should be equal to a constant, and only then can they be written in this manner. Now, what should that constant be? We don't know, and that is the whole point of this separation of variables, or this method that I'm trying to show you here. That we need to derive that constant. So the constant is typically written as, in this case, the way I've written, and I already know what the solution should be, so I'm writing in a special way, and I'll show you maybe in a few minutes why I did this. So I can write this as minus lambda square, ensuring that lambda square is a positive number, and a negative sign, the negative sign that I include ensures that we are able to satisfy the boundary conditions. Negative sign ensures that the boundary conditions are satisfied. This I'll be able to show you very quickly, that what, or rather, what happens if it's negative lambda square. When you can try separately taking it as a positive lambda, as a plus lambda square, and then you see that the boundary conditions basically give you a trivial solution, which is that theta can actually be 0 everywhere. That is not a solution that we are concerned with, and that's also not physically correct. So let me show you what minus lambda square does. Okay, so now we have two equations in the same, from this differential equation coming out. So we have 1 by x d2x dx square minus lambda to be equal to minus lambda square, and then we have minus 1 by y d2y dy square to be minus lambda square. So we can individually solve these equations. So we have d2x dx square plus lambda square x to be 0, which means that x of x would be some, let's say, c1, and this is the equation of a simple harmonic motion. So this just becomes c1 cosine lambda x plus c2 sine lambda x, and the second equation we have is d2y dy square minus lambda square y is 0, which means y of y, this is the same as the fin equation, would be some c3 e to the power lambda y plus c4 e to the power minus lambda y. And so we can write the solution to the problem theta xy is the product of x and y. So that becomes c1 cosine lambda x plus c2 sine lambda x times c3 e to the power lambda y plus c4 e to the power minus lambda y. So we have four unknowns now, actually five, because lambda is also not known yet, and we need to find out what these values are to be able to get the solution to the problem that we started with. So let's apply boundary conditions to this problem. So the first boundary condition is that theta at x0 comma y, which is the first vertical phase, that was 0. Now if I put x equal to 0, you can see that from the solution this term will vanish, because x equal to 0 will give me this is 0. There's nothing, no change to this. But then we have c1 times this number to be 0, and clearly the only way that is possible is if c1 is 0. So we get the first constant, or the first constant of integration from this method. The second boundary condition I can apply is that c2, or rather theta, at let's say x comma y0 is 0, which is the bottom phase now. Now what does this mean? This would mean anyway c1 is gone now from the problem. We'll have c2 sine lambda x times c3 plus c4 to be 0. So this means that c3 to be equal to minus c4 is the second equation. The third boundary condition is the most interesting, I will say. The third boundary condition is theta at x equal to L, and for all y is 0. This means we have c2 sine lambda L times, I can pull out c3 from that from the second one. So we have c times c3 e to the power lambda y minus e to the power minus lambda y to be 0. So clearly for this to be 0, okay, for this equation to be 0, this cannot be 0, because this is anyway, this has a y dependence on it. C3 and C2 cannot be 0. Okay, because if C3 and C2 are 0, then again we get theta xy to be 0 everywhere. So it doesn't solve the, we get basically, as I'm saying, a trivial solution that it satisfies the governing equation, but it will not satisfy the boundary condition, which is the last boundary condition I'm yet to apply. Okay, so the only way this can be satisfied is if sine lambda L was 0. And that means that lambda should be n pi by L, where n takes on integer values, because that is the argument for sine to be going to 0. Now, because I hope this is clear. Is this okay? So I didn't even interrupt, but let me stop and ask now. Is this all okay so far? So since lambda depends on a select, on this selection of n, on the integer, I'm just going to write this as lambda with subscript n to denote that this is, lambda corresponding to a given value of n. Okay, so if n is maybe 1, it becomes lambda 1. If n is 2, it becomes lambda 2, and so on and so forth. But in those cases, at least this is, we know that the value of lambda will be in terms of L, inverse of L. Now, in maths, when you did this, I'm hoping you did this, at least we did when we were students, so I don't know. I don't know how it's going now. This is what is called as an eigenvalue equation. And it's not eigenvalue equation like you see in matrices. Okay. And this lambda is what is called as an eigenvalue in this case. So we've set up an eigenvalue problem for solving this two-dimensional heat conduction problem. So the idea of taking a negative lambda square, now I go back to that step. I took a minus lambda square there. It was because I knew that the eigenvalue problem has to be set up in X because the boundary conditions are homogeneous in X. They are not homogeneous in Y. There is a non-homogeneity in boundary conditions because I know that this boundary condition, if you see this, theta at X comma W is 1. This will not allow me to set up an eigenvalue problem. Only this is going to allow me to solve. If I had a positive lambda square here, then this X would have actually given me an e to the power lambda X kind of solution, and this would have given me a sine lambda x and a sine lambda y and cosine lambda y type of solution, and that will still not satisfy the boundary, the overall boundary conditions. So I know ahead of time, having done this, so many times, we know that this is what is going to work and what is not going to work. As a beginner, the rule of thumb is that we look at which side, there is homogeneity in boundary conditions and which side there is not. So that helps in getting this value of lambda. If you don't follow this, don't worry. If you end up doing a stupid thing like me doing a PhD, then you will understand this better. But anyway, this is what you end up getting. Now we need to apply the final boundary conditions, or rather, before I apply the final boundary condition, now we know that lambdas are actually many in number, because this will go to infinity. Lambdas will go to from one, to infinity, lambda infinity, as n goes from 1 to infinity. So what I'm going to do is I'm going to write this solution now slightly differently. This solution I'm going to write slightly differently now. So I'm going to write this as in terms of the new lambda parameter that we have defined. So I'll write theta x comma y to be, let's say, noticing that C3 and C4 were equal and opposite of each other in terms of sign. So C3 was minus C4 and C1 is already 0. I can combine C2 and C3 into one coefficient. So I will write this as some Cn prime sine n pi x by L, which was sine. Remember, there was a sine lambda x. Lambda is just n pi by L into e to the power n pi y by L minus e to the power minus n pi y by L, because I know that the solution is now dependent on the value of n, which comes from the eigenvalue equation. Okay, and the reason I wrote it this way is because now I know that this e to the power n pi y by L minus e to the power minus n pi y by L is actually written in terms of a sine hyperbolic, or can be written in terms of a sine hyperbolic function of that argument, which is n pi y by L. So I can write this as 2 Cn prime, except 2 is another constant. I don't need to worry about it. So I'll just write this as Cn sine n pi x by L into sine hyperbolic of n pi y by L. So that gives me a more compact form of the solution. Now we get to another aspect about linear differential equations and their solutions. So note that the governing equation that we solved was actually a linear equation, and we've got a solution which has some n dependence. N and n is, then there are many solutions basically. Depending on what value of n you choose, you still satisfy the differential equation. So we can write the final solution in terms of a linear combination of all these solutions, which are infinite number of solutions. So I can write theta xy to be a linear combination of all these solution. That becomes the general solution to the problem now. Okay, so that is for linear differential equations. We can always write them as if we have multiple solutions, the solution that we were looking for should be in terms of all these, linear combination of these solutions. So now we get to the last part, which is on how do we determine these coefficients Cn. And now they are infinite, by the way. They're infinite, and I only have one more condition left, which is the fourth boundary condition. I know that theta at x comma w is 1. Okay, so if I put that, let's say the last boundary condition, so I get theta x comma w, which is 1, is equal to n from 1 to infinity Cn sine n pi x by L sine hyperbolic n pi W by L. So now we see a challenge. I hope you see it, that there are infinite number of unknowns, but there is only one equation. So maybe, theoretically, maybe somebody might think that we cannot solve this. Now there's a very elegant way of figuring out CNs from this just one equation. This uses the principle of orthogonality of trigonometric functions. And by orthogonality, what I mean here is that if you look at the product, let's say in this specific case, the domain goes from 0 to L. Okay, the length x goes from 0 to L. If I look at sine n pi x by L, and so integration of, let's say, this function sine n pi x by L into sine m pi x by L dx. If I look at integrating this function where m is, let's say, or rather for some m and n, where m and n are integers, so this function is actually 0 if m is not equal to n, and it's non-zero only if m and n are equal. So you can derive, again, please try this. Okay, try and use some m and n. I mean, you can just do it in a very general sense. See that it can actually it comes out to be 0 only, or it comes out 0 if m is not equal to n. It is non-zero only when the two integers are the same. And so the two integers are, by the way, I should say, m and n being positive integers, not just any number. They have to be integers for this to work out. And thankfully, in our problem, the way we have set it up, n and n, I mean, n is actually an integer value. The argument has some integer times pi x by L. So we can use this idea to now calculate what would be CNs. Because if you see now in this equation that I have, a single equation, I can multiply the whole equation by some specific value of sine n pi x by L. So maybe I multiply it by, sine pi x by L when n is 1. If I multiply and then integrate over 0 to L, then I would actually get C1 times something on the right hand side. Everything else will be 0. And I would have another, I would have an integral on the left hand side, which we can easily calculate. Integral of sine something is not very difficult. So again, then I can go to C2. To obtain C2, I can do sine 2 pi x by L, multiply both sides, and then, integrate, and then so I get C2. So I can keep doing that. So if you do this, so multiply by a specific value of n, what we get is, and I'm going to now try and take a little liberty with my symbols. So let's say I multiply both sides by sine n pi x by L and multiply. So we'll get 1 times sine n pi x by L dx to be equal to Cn 0 to L sine square n pi x by L into sine hyperbolic n pi W by L, which is anyway a constant, dx. Okay. And so I can integrate both left and right hand side. This I'm leaving to you as an exercise. So Cn in this case will come out to be 2 by n pi times 1 plus minus 1 to the power n plus 1 divided by sine hyperbolic of n pi W by L. So we can then obtain these specific coefficients, and now we can assemble the solution. So finally we have the solution, which is, or which would look like theta of x comma y. So summation n going from 1 to infinity 2 by n pi 1 plus minus 1 to the power n plus 1 times sine n pi x by L sine hyperbolic n pi y by L, and the whole thing divided by sine hyperbolic n pi w by L. So that becomes the final solution, which you can now see is in the form of an infinite series.
Sir,
Yeah,
sir, how, if we have written the solution as an infinite series, how do we know that the solution will converge?
that's a good point. What do you think?
Sir, we have
How do we check?
imposed like we have imposed no restrictions on the convergence or divergence of the series yet.
No,
So
yeah, that's so. The thing is, do you remember? Okay, let me put it this way. Do you you've done Fourier analysis, right? Fourier series
no, sir.
in maths, right? You would have done Fourier series.
No, sir.
Not yet. Okay. Have you done a course on controls?
No, sir.
Have you done Laplace transforms?
Yes, sir.
Okay. Okay, at least some technique you've done. Okay, so typically in Fourier series and Laplace transforms, let me put Fourier series is also one way of, it's a similar concept to Laplace transform. Fourier series essentially looks at, it works on the idea of describing one solution or let's say a function in the form of many sine and cosine functions which have frequencies which are progressively increasing in multiples of each other. So you have a fundamental frequency and then you have these higher frequencies which are multiples of that frequency. So those kinds of series, which is, and this is actually a special case of a Fourier series, because there is this, you can think of it this way, that this is a Fourier series which has this frequency which comes in here because of this sign dependence. So these kinds of series typically converge. And the reason I can also tell you is that there are tests of convergence which are basically, there are different ways of finding out whether a series converges or not. One of the ways is to, of course, look at whether the coefficients of that series are actually bounded. So in this case, if you look at this coefficient, which is what will actually can lead to supposedly divergence of the series, this is actually progressively becoming smaller as the series increases or as you go into higher terms. Okay. Do you see this? Because n is going to infinity and this number is not going to change.
Yes, sir.
This is just minus 1 to the power n plus 1. So it will keep flipping from minus 1 to plus 1. That's it. It
Yes,
will
sir.
not do anything else. So this series, the final terms, in the eventual part, let's say if you go to very large n, this number will actually keep shrinking. The coefficient will keep shrinking. So I can say in that from a very simple, this example, that the series will actually converge. Now, in many cases it does not. There are different tests to ensure, or to calculate whether or not calculate, but to check whether the series converges or not. Such is not the case. Such is not the case typically with Fourier type of analysis. And if you do maybe a course on controls, you will see this. I think maybe if not this semester, maybe next semester you'll do a course on control theory. There you'll also see why this specifically converges. But this series, if you see it, you can easily make out that it will actually converge because the n factor comes in the denominator. Okay, and there is no dependence of n otherwise, which will potentially make this series diverge. Does it make sense, or I don't know? Are you is that clear?
Yes, sir. Yes, sir.
Okay. Okay. So that is the solution for this problem. And now the method of separation of variables works here, as I said, because of the special boundary conditions that were given to us, and also because the equation was homogeneous, or not homogeneous and linear. It is not always the case. If you had in this problem, if you just add the heat generation term, you can make out that it will not lead to a solution. You will encounter difficulties straight away when you're trying to separate two variables. You're trying to separate x dependence and y dependence, you will actually get stuck. So it works in very special cases. It does not work everywhere, and so we have only special solutions. For more complicated problems, typically numerical methods are employed. In chapter 4 of your book, if I remember, there is some discussion on how numerical methods can be used to solve these kinds of problems. I am not covering it specifically because it is not, those are topics that are dealt in more in higher level courses. So I'm going to limit myself to just looking at analytical solutions for this course. Okay, so this is all I had to say about two-dimensional heat transfer. There's nothing more I want to say about two-dimensional heat conduction problems. Now, but I can also say that very similar to this, the same idea can also be applied to three-dimensional heat transfer. If instead of a square, or a rectangle, we had a, some kind of a cubical geometry where the boundary conditions were again homogeneous everywhere except at one surface, I can still obtain this kind of a solution. Okay, so this is something for your information, that it can still be done as long as the governing equation is homogeneous, the boundary conditions are homogeneous, and inhomogeneity only occurs on one side, not more than one side. But there is a trick here, by the way, that I should say. Although you are for an undergraduate class, this is a lot of information. Some people might even find this boring, but just for somebody who is very inquisitive and may be thinking ahead, because the governing equation was linear, I can, and in case, let's say I had inhomogeneity or non-homogeneous boundary conditions on two surfaces, I could still make it as, I could still solve the problem by using the method of superposition. That I could divide the problem into two problems, each having only one inhomogeneity in boundary condition. And then when I get two solutions, I can combine the two solutions and then I get the solution to the first problem. So if it makes sense, good. But if it doesn't, that's okay. You don't lose anything. You may see this one day if you end up taking any higher level course on heat transfer. Okay, so the method of superposition is always there. Okay, so let's move on. So we've looked at one-dimensional steady-state heat conduction. We've looked at two-dimensional steady-state heat conduction. Now let me bring our attention to transient conduction. So what happens when you have temperature dependence, or you want to know how things behave when you have or situations, how in situations when you have time dependence coming in, how do you derive solutions, or how do you come up with some estimates of how a system maybe heats up or it cools. So we'll look at we'll start with a very special case of transient conduction, in which, let's say, or let's put the problem in this way. Let me put the problem, then I'll explain what I'm going to do with this specific case. Let's say we have a tank of some fluid. So the tank is filled with some fluid, and the fluid has some temperature, maybe T infinity. Okay, and I had a solid, which was a hot solid, and I at T0, I put it inside this fluid. So maybe the solid was some potato, who knows what else it is. So maybe some ball or some material. So let's say this solid had a temperature uh, Tx comma 0. So that means temperature at x, or I should say x vector. I should not say x. So temperature for at all points at time T0 was, let's say, Ti, and let's say Ti was more than T infinity. So we had it's sort of saying that, when you quench, and I think I can put this example to you, not to your juniors. If you did your first year course in the workshop, manufacturing processes, you would have, I don't know, during my time, we used to, I think in the forging shop, we used to given a piece of a billet, and we had to really put it down, hammer it down to one particular shape. So we would frequently, heat it and then quench it, or stuff like that. So if you go back to that example, so if I say that you have a hot metal and you suddenly dip it into, let's say, water, and now you're quenching it, you're cooling it down. So I want to now know at what rate is heat is being removed from that material in that, let's say, the quenching process. The other way around is also possible, that let's say you put this piece of metal or any material into maybe a hot furnace. So the surrounding fluid is hotter and the surface is cooler. So at what rate is heat being brought into this material? So either way, we're looking at heat transfer rate. So that is a question. Okay, so we're looking at quantifying this behavior. So how does it change with time? So what I'm going to start with is a special case. The special case that I'm dealing with, or I'll work with, is a consideration that I'm going to assume. Let's say it's a 2D body. Let's say it's a 2D problem. Even if 3D, it doesn't matter. It would be the same thing. Let's say the temperature gradients inside the solid, let's say dt dx, dt dy, are nearly zero. They're insignificant. What it means is that the solid is sort of behaving at the same temperature. Let's say for now spatial gradients are zero, which means that the temperature, which was a function of typically x comma t, okay, space and time, I am going to approximate that as a function of time only. Let's say we will see whether this works or not, but for now, let's say this is something that we are assuming. Okay, as I said, the fluid temperature is T infinity, which is less than Ti, and I am interested in knowing how this solid cools with time. Okay, what is its temperature, especially the surface temperature, because that is something that I can measure. So I'm interested in knowing, let's say, temperature of the surface at some time, maybe 1 minute after I put it inside this fluid, or maybe an hour afterwards, or even that I want to know at after how much time can I say that this solid has reached a steady state temperature. All those kinds of problems that I need to address. Okay, so we are going to assume that the solid temperature is fairly uniform for now, and we will apply our energy balance as usual to try and come up with the temperature dependence as a function of time. So I'm going to define a control surface around this solid. So this is the solid becomes a control volume, and the surface becomes a control surface. And I'm going to apply energy conservation on this control volume. So energy conservation would mean that E dot in minus E dot out plus E dot generation is E dot storage. Now note that I didn't say anything about generation, but we are saying in this case generation is zero. So this is not there. Now the solid let's say it was initially at a higher temperature, there is nothing coming in, from this. If it's at a higher temperature, then it must be losing heat. So E dot in is zero. What is E dot out? So considering that there's a fluid surrounding the solid, there must be heat exchange because of convection. So we can write E dot out to be H AS, where AS is the surface area of the solid, whatever shape it may be, times, let's say, T minus T infinity from Newton's law of cooling. That is the rate at which heat is going out, and that should be equal to the rate at which the storage term is changing. So the storage term would be mCp dt. So the mass can be written as rho times its volume. Cp, so the heat capacity I'm just going to write as C dt. So that is basic energy conservation for this solid. Now, this is actually a simple linear differential equation, and it's also first order. So I can, just to make life easier, I will again define a variable theta, which is T minus T infinity, which means we have minus HAS theta to be rho Vc d theta dt. So let's shift the variables in a certain way. So we have d theta by theta to be equal to minus HAS by rho Vc dt. So we can now integrate over, let's say, some temperature theta I to some unknown temperature theta, which is a function of time, from 0 to t, to some general time t. So we'll get theta to be theta I times exponential minus HAS by rho Vc into t. So that basically this equation now tells us that we can calculate the temperature as a function of time. So remember theta was T minus T infinity, and theta I is Ti minus T infinity. So I can divide this thing by Ti minus T infinity. This is equal to exponential of minus HAS rho Vc times T. That becomes the response of this solid to this sudden change in its surroundings, I can say. Now this is an easy to use equation, right? Because we don't need anything. If I tell you that, calculate the temperature maybe after 1 minute, I can just plug in T to be 1 minute and I can get the temperature after 1 minute. If I put the question other way around, I say that maybe the surface temperature is measured to be some, degree Kelvin, so what determine the time after which this measurement has been made. Again, from the same equation, I can determine what time it would be. Okay. So this is the simplest possible model, and this model is what is called as a lumped capacitance model. Typically in transient systems, this is the first step we follow. So the lumped capacitance method is the first step we follow typically when we deal with any transient problem, because this is allows us to calculate the solution fairly easily. So let me say a few things before I look at the limitations of this method. First thing you should notice is, because this left hand side is anyway a non-dimensional number, the right hand side is an exponential of something. So clearly, because there's a time variable there, clearly rho Vc by HAS should have units of time. Okay, this has units of time. So let me define this as some tau of t, sort of like a time constant. And what is this time constant? So I can write this in a slightly more different way. I can write this as 1 by HAS into rho Vc. And now I note that 1 by HAS is sort of the resistance to convection. So I will say this is R, let's say T, resistance to convection. And rho Vc is essentially mass into specific heat. So it is like thermal capacity of the system, of the solid. So I'm going to write this as thermal capacitance. So it's R into C. Now the choice of using R and C is again, comes from electrical circuits. So this problem is actually very similar to discharge of a capacitor across a resistor. So there's a capacitor C with resistance and attached in series to R. So if you charge a capacitor and you discharge it, the response is actually given by the same equation, except of course we don't write in terms of h and this. You actually have response comes as h e to the power minus t by tau, where tau becomes r into c. So the response is similar to electrical circuits, where we can write this as maybe exponential of minus t by rt ct. So similar ideas are again commonly used. So now let me address this part about whether this, how good is this model or this method, and when is this valid. Now to show to you how when this is valid, let me take another example. Let's say we have a plain slab, okay, which is exposed to a surrounding fluid, which has heat transfer coefficient, let's say h, temperature is let's say T infinity. Let's say the slab has zero heat generation. Let's say the thermal conductivity is constant. Say the slab has thickness maybe L, and we're dealing with this problem. So maybe the cross section area is A, although it won't matter, but still let's say the cross section area is A. Let's say we want to look at the transient response, or rather the steady state response, or the steady state temperature profile in this system saying that T infinity is, let's say, more than the back end temperature of the solid. Let's say the solid has surfaces A and B, so the back end temperature is TS2. Let's just say, it won't matter, but I'm just saying for making an argument. So clearly heat will flow from left to right. If T infinity is more than TS2, we will have heat transfer taking place from the higher temperature to the lower temperature. And we're looking at steady state distribution. So what you expect at steady state is, if I draw the temperature profile, and let's say TS1 is maybe the temperature here on this surface, so we will have a temperature profile which would look something like this. So this is going to T infinity. From T infinity it goes to TS1. From TS1 it goes to TS2. Now, what is the boundary condition on this surface A? This is a special surface. What is the boundary condition here? Boundary condition here would have been that the heat flow or the heat flux because of convection, which is HA T infinity minus TS1, should be equal to the conduction heat transfer rate. But just because Q dot is 0, we can write that the heat flux or the heat transfer through the slab can be written using a linear expression or linear temperature variation. So this can be written as Ka by L Ts1 minus Ts2. So let me do a little rearrangement here. So I can write Ts1 minus Ts2 by T infinity minus Ts1 to be equal to L by Ka divided by 1 by HA. Yeah. Because I'm going to take them separate. So I hope this is clear. Basically, it should be HA by K by L, but then I flip, because it's HA in the numerator, I can flip it to 1 by HA in the denominator. Now, what are these numbers? L by Ka is actually the resistance to conduction, and 1 by HA is the resistance to convection. So L by K is the resistance to conduction in the solid. 1 by HA is the resistance to convection at the solid and the fluid interface. So in case, let's say, if R conduction was much less than R convection, the conduction resistance was very small as compared to convection resistance, then this number that we are saying R conduction by R convection would be much less than 1, which would mean that Ts1 minus Ts2 would be much less than T infinity minus Ts1. And what does it imply? If Ts1 minus Ts2 is much less than T infinity minus Ts1, it means that the temperature variation in the solid would be marginal as compared to temperature variation outside the solid. So the outside the solid is the boundary layer variation. This is actually the thermal boundary layer variation. So this variation would be much larger as compared to this variation, which means I can sort of assume that the whole solid is at the same temperature. I mean, it's an assumption, but I can assume that the spatial variation of temperature inside the solid is minimal as compared to, or negligible as compared to, variation outside the solid in the boundary layer. And that is the whole essence of this lumped capacitance method, that we neglect spatial variation if the conduction resistance is much less as compared to convection resistance. Now, incidentally, this number R conduction by R convection, which I have written as L by K by 1 by HA, can also be written as HL by K, because H will come up, area is anyway going to get cancelled. So it's HL by K. Remember, K is the conductivity of the solid, not the fluid. H is the heat transfer coefficient. This number is called as a Biot number. And Biot was the one who developed this theory, so it's given credit to him. BI. So we are saying for the lumped capacitance model, Biot number should be much less than 1, and then this theory works. And then we can say that temperature as a function of x comma t is only a function of t, or we can approximate that. Okay. Anyway, okay, let me stop here now.